All right, everyone, welcome. Thank you for showing up for your learning, for locating yourself in such a way as to maximize the value of the lesson. So here we go. Let's take a look at how we can use a quadratic formula to solve some of these types of situations, and also to really analyze the behavior and properties of some of these quadratic functions. Let's keep going. So let's get started. So here we have a situation where there's a model rocket, and we've got an equation. So this equation that's going to come in handy. It's useful, right? And what's the equation telling us? Well, it tells us the height. The height is the y value, how tall, how high it goes. And the t value is how many seconds it takes for it to get there. So let's take a look at how we could find the initial height of the rocket. Well, what's time at the initial value? How many seconds have gone by before the rocket is launched? Zero. So we want to know what the height of this rocket is at zero. There's another word for that. It's the y-intercept. What's the y-intercept of this function? Yeah, it's just 1.1. This one is just that easy. We could just copy it out, and we could do this a little bit more, like h of t is equal to negative 4.9 t squared. And if you're not writing this down, I don't blame you, because if you know what I'm about to do, you'll be like, well, I know you're going to substitute 0 in for t, Mr. Jennings, and that's going to make this 0 and that 0, and then plus 1.1, right? Because if I'm multiplying by 0 here and I'm multiplying by 0 there, both of those terms are going to be 0. So therefore, and we do want to have these communication things in our work. We want to interpret the values that we find and tell our audience what they mean. Therefore, the initial height of the rocket is 1.1 meters. Done. Okay, just that straightforward. We just read that c value, and that will tell us the initial height of the rocket. So, supposing we wanted to know the answer to a more complex problem, like how long is it going to take for that rocket to go up, come down, and hit the ground? How much time will have gone by horizontally, kind of, because x is our time measurement. So here, I really encourage you to have a good visualization of these things. All right. If we take a look at the function here, h of t, we have a positive b value, a positive a value, a negative a value, and a positive b value, and then the c value of 1.1. So I know it starts at 1.1. It's going up as it crosses the y-axis, but it's a parabola opening downwards. So it's going to have a shape something like this. Okay. And I'm told that by the equation. I can just look at that equation, visualize it right away. If I want to know how long was the rocket in the air for, this is time 0, and this will be time how long the rocket was in the air for, right there. So I want to find this root. Having this visualization of the quadratic tells me I'm looking for elapsed time between there and there. I need to know that root. So let's find the root. We're going to make a little chart with a equals negative 4.9. I'm actually going to just change my pen here, make it a little smaller, and zoom in. People have the first one, right? I can zoom in a little bit. Here we go. A is equal to negative 4.9. Oh, I should have the function copied out. There we go. B is equal to 16. And C is equal to 1.1. All right? These are our numbers for the quadratic formula. Next step, copy it out. Now I'm going to zoom so I can do the work a little smaller. So we're going to have our T is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Copy it out every time and then substitute carefully. So let's go. The time is going to be negative 16 plus or minus the square root of 16 squared. I'm just following this recipe, putting this ingredients list together in the prescribed positions. So just follow your recipe. 16 squared minus 4. Minus 4 multiplied by a. Well, a is negative 4.9, so put a negative 4.9. And then multiplied by c, so c is 1.1. So multiply by 1.1. Cool. This should continue on over the whole thing. All divided by 2 times a. So that's 2 times negative 4.9. All right, let's keep going. T is going to equal negative 16 plus or minus, well, what's 16 squared? I think it's like 256. Let's see. I don't really have it memorized. It is?
Yeah.
256? Okay, cool. I do have it memorized. 256 is 16 squared. Maybe I should do these lines in different colors. Oh man, I lost my buttons. 256 minus 4 times 4.9 times 1.1. Well, let's do that on a calculator. Calculator. 4.9, but it's negative. So there's my negative button. Times 1.1 times, just to be clear, negative 4 here. Negative 4 times negative 4.9 times 1.1. So I'm going to multiply by 4, but it's negative. Will give me 21.56. Come on, man. Oh, man. Just save. I got to close it and reopen it. That's really annoying. Let's see if I still have my notes. If I don't, you will see me be a little bit annoyed. There we go. Got everything still. Okay, here we are. Okay, so that number, again, was 21.56. Let's go ahead and put that number in right here. Oops. 256 plus, get a finer pen. Struggle with the technology, my goodness, plus 21.56. All divided by 2 times negative 4.9. Well, that's negative 9.8. Okay. Zoom in again a little bit to see it better. Okay. Now do it. So we're going to add 256 to that number. Just going to move this over here so you can see what I'm up to. We're going to add 256. And this is what we're going to have inside the square root. Let's find the square root of that. Boop. So that's 16.66. Oh my goodness. So we have time is equal to negative 16 plus or minus 16.66 divided by negative 9.8. All right. At this point, we can divide this up into two different things and do the plus and the minus. So t will be equal to negative 16 plus 16.66 over negative 9.8, or t will be equal to negative 16 minus 16.66 over negative 9.8. Evaluate each independently. So here we go. This is 16.66. I am going to do the first one, subtract 16. That gives me this number. Divide that number by, move my useless face. Remove it. There we go. Divide it by 9.8, but it's negative. Equals, so the first one is negative 0.067. So this one here, t is equal to negative 0.07. Okay, that's one of my t values. That came from this. Let's do this one here. Negative 0.067. Well, I'm just going to call that negative 0.07. I round that to the nearest hundredth of a second. This other one here, let's move this over. We will have 16, but it's negative. Subtract 16.66, but it's negative, equals, well, that's not correct. Let me do that again, clear. 16, but it's negative. subtract 16.66, and that's just fine, equals this, divided by 9.8, but it's also negative, equals 3.33. So this is t equals 3.33. That's our other value. It came from evaluating that on a calculator. So let's go back to our visualization. If I move this over, and it will show me. So what I'm finding here is that there's one value of t that satisfied the quadratic equation, and it was negative. It was back here. It was before time began. In fact, it was 7/100ths of a second before time began. What you can imagine is the rocket started at 1.1 meters high and went up. If you went back in time, it would have gone that way. And it would have taken 7/100ths of a second to hit the ground from that very low height. It's going to go quite high and then come down. Let's find out where. All right. So when? Well, it came down after 3.33 seconds. This value here is the other one. That's 3.33. So therefore, the rocket was in the air for 3.33 seconds. Because it clearly wasn't in the air for 7/100ths of a second. That would have been if we aimed the rocket downwards and it went boom. It would have been a very short flight with a hard landing. Actually, the landing, if you ignore air resistance, the landing would have been just as hard on the other end. It would have been exactly the same hard, but it's not because of air resistance. Let's keep going. Now, let's say we want to know if the rocket reaches a height of 60 meters. There's a couple ways we could answer this. We could find the vertex and then find out how high the vertex is. And if it's higher than 60, we would have an answer of yes. But then we don't know how long is it at 60 meters. We wouldn't be able to answer the second part of the question. Okay? What we need to look at is here our visualization. If we find this vertex is above 60 and 60 is somewhere like that, we want to know how long does it take from here to here. What's the gap between those numbers? And I'll show you how to find an answer to a question such as this. We're going to create a new quadratic. All right. So here I'm going to zoom out. I'm going to write this in my writing tool here with text. We're going to go over here in black, copy the function. We have h of t is equal to negative 4.9 t squared, but I can't do a squared here, very annoying, plus 16t plus 1.1. Okay. So there's my function. Let's make the font a little bigger. All right. And now what I want to know is, let's zoom in. There we go. I didn't lose my drawing tools this time for some reason. Cool. And I'm just going to square that because it's going to bug me if it's not squared. So I'm just going to copy out the formula. And I want to know, will this reach a height of 60 meters? So put that in for the height. 60 equals negative 4.9 t squared plus 16t plus 1.1. Okay. Now this equation is saying the height is equal to 60 when t, some amount of time, has gone by. Let's find the amount of time. If we get an impossible amount of time, like some kind of time that doesn't exist in our universe, then we know it's never that high. This is how we do it. First, we have to set this equation equal to 0. To use the quadratic formula, which is my tool of choice for a problem like this, I need 0 equals t squared plus blah, 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 blah. So let's make this equal to 0 with inverse operations. I'm going to go in here, get my inverse operations pen, and subtract 60 from each side. Then I will get the equation 0 is equal to negative 4.9 t squared plus 16t minus 58.9. Okay, I took 60 and I took 1.1, I subtracted 60, I got negative 58.9. Maybe your calculator tells you the same thing. Okay? Now I can use the quadratic formula with these new numbers. Let's find out if the quadratic formula tells us if we have any roots at all. If the quadratic formula says there are 0 roots, then it never gets that high. If it tells us there's 1 and exactly 1 root, it gets that high, but only for an instant. That's the vertex. And if there's 2 roots, then we'll have a gap of time where it's at least 60 centimeters tall. Sorry, 60 meters high in the air. So let's find out. Make our little chart with our A, B, and C. So our A is here, negative 4.9. Our B is still 16. And our C is now negative 58.9. It really doesn't look good. Okay, let's check out why. All right. So here, you want to do the whole quadratic formula, or do you just want to answer the first part of the question? Does the rocket ever reach the height? It's a simpler question, yes or no. Let's answer that one. The tool we need is the discriminant. This part of the quadratic formula, b squared minus 4ac. This is the part that's normally under the square root. If this is ever negative, then I know there's no real solutions. So let's see if this is going to be negative. B squared, so we're going to have 16 squared minus 4 times negative 4.9 times negative 58.9. You see it now? B squared minus 4ac. See how this is going to be negative? Just get like an intuitive sense that this number is still negative because it's got 1, 2, 3 negative signs in it. When I multiply 3 negatives together, I get a negative back because it's an odd number of negatives. Here's my classic demonstration. Here's 1 negative, here's 2 negatives, here's 3 negatives. The final positions of the lights is in the negative position. Here's a 4th negative to give you something to write by. Okay? So that's an even number of negatives. If you ever have an even number of multiplying negatives, the answer is even. An odd number, it's odd. So that number is going to be negative, and it's much bigger than 16 squared. Look, that number 58.9 is going to multiply this number here even bigger. 4 times about 5, it's already about 20. So this is like 20 times 60, much bigger than 16 times 16. So let's evaluate it. Okay, we can always just, find out what exactly it is. 16 squared is indeed 256 minus bracket 4 times 4.9, but it's negative, times 58.9, but it's negative, and the bracket equals negative number, big time negative. So since b squared minus 4ac is much less than 0, therefore the rocket never reaches the height of 60 meters. Oh well. Now let's take a look in Desmos and confirm that was true. Okay, so I'll leave this for just a second and you can evaluate. Note that if this was greater than 0, if this was some number that we can work with, then we would use a quadratic formula to find those 2 roots, and that would tell us how long it was at that height for. So let's go ahead and dump this formula into the quadratic, into the Desmos here. As you can see, I have a number of Desmos. Oh, only one Desmos tab open right now. So we were looking at h of t, which was equal to negative 4.9 t squared plus 16t, there we go, plus 1.1. And we have to zoom out to find how high does this go? Notice it never gets anywhere near 60 meters high. Actually, it's a very disappointing rocket flight. It only goes 14 meters in the air, and it comes down after 3.3 seconds, just like we calculated. When we set the bar at how long does it 60 meters or higher, it's never 60 meters or higher. So that confirms everything we just found using the quadratic formula. Let's keep going to another problem. Any questions about this type of problem? It's use the quadratic formula, but have a picture of what you're looking at in your mind, or sketch a picture in your mind so that you can interpret the values that the quadratic formula is giving you. What do they mean? Let's take a look at this example. If we're building a factory on a lot that measures 80 meters by 60 meters, anytime you see something like this, you're going to label your sides. So this is 60 meters and this is 80 meters. Okay, that's the lot. And we want the area of the factory that's in here, so this is the factory, to be equal to the area of the lawn that's surrounding it. And then we want to know how wide is the lawn. All right? So I don't know things like how wide the factory is yet. So let's call its width here x. If I know x, and I know that x is the same ratio over there, then I know that this must be 80 over 60 x wide here. Notice that that would have the same ratio. This number will be bigger. No matter what number I put in for x, this number would be bigger than that number by a factor 80 divided by 60. This is bigger than that by 80 divided by 60. So there you go. 80 over 60 is a fraction that will reduce. Yeah, you say 1.3 repeating? Yeah, I call it 4/3, but same. Good. So this is equal to 4/3 x. Now the factory, which is x times 4/3 x, has the same dimensions as the yard, 60 by 80. Okay? And now, if we know that the area of the factory is equal to the area of the lawn, we're moving towards answering this question. Notice I'm just taking a look at the lawn of uniform width and that it's equal to the area of the factory. So the two areas are equal. So I write an equation. Area of factory equals area of lawn. I know the area of a rectangle. Here are my two dimensions. The area of the factory is just going to be length times width. Okay. The area of the lawn will be the 60 by 80, 60 multiplied by 80 minus the length times the width of the factory. The area of the lawn is the area of the whole lot minus the area of the factory. I want both sides of this equation to equal one another. Let's take a look. I can substitute in for L and W my values of x and 4/3 x. So the length was 4/3 x. The width was x. And that's equal to 60 times 80. Well, 60 times 80 is 4,800. Minus 4/3 x times x. Oh man, why is this not going to solve for me? And I have some other things that I need to do here with this problem to get it to go. I need to note that this here is the same as that there. Yeah, I'm doing this backwards. I'm doing this in the wrong way. So what I notice here is my algebra is just going to cancel out. Yeah, it's strange. So actually, no, that's interesting because the area of the factory and the area of the lawn, they're each half of this. So actually, this is not bad. What I can do is if I know that the factory and the lawn have the same area, just say that the factory, its area is equal to 480 divided by 2. That's going to do it. And then I'm going to have 4/3, the size of the factory, multiplied by x, is equal to 2,400. And this will solve. That's no problem. That's going to go. So let's turn this into a quadratic. So we have 4/3 x times x. That's just 4/3 x squared. And then I'm going to use my inverse operations pen to set this all equal to 0, minus 2,400 on both sides. Okay, and that's going to give me minus 2,400 over there. And then I have my A's, B's, and C's. Minus 2,400, okay, equals 0. Here is my quadratic that I can solve, and it will tell me the width of x once I find the value for x that makes that true. So let's make our little chart. A equals 4 over 3. B equals 0. There's no B value here. And C equals negative 2,400. So now let's apply the quadratic formula. We have the quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. All right, now let's substitute in. Here we go. X is equal to, there's no b value, it's just 0. So I just have plus or minus the square root of b squared. So b is 0, so that's nothing. Minus 4 times a, which is 4 over 3, times negative 240. Okay, all divided by, that's an ugly 4. Yeah, that's a better 4. Divided by 3, that's me substituting in a. All divided by 2 multiplied by 4 over 3. And now 4 times all of this, so let's do all that. Negative 240 divided by 3 gives me negative 800. Multiplied by 4 gives me 3,200. Multiplied by 4 gives me 1,208,000. 128,000. So do it on a calculator and confirm. So just going to put what's in the square root there inside my calculator. So I have 4, but it's negative, and I'm going to multiply by, put it in brackets, 4 divided by 3, that's 4/3, and bracket, multiply by 2,400, but it's negative, equals, that's what goes into the square root there, 12,800. It's a good thing I confirmed. Take the square root of that, gives me 113, and then divide that by 2, and divide that by 4 divided by 3, equals 42.42. So x is equal to 42.4 meters. All right. Now go back to your diagram and see if that looks like it makes sense. If that was about 42 meters, this would be a bit longer than that, and that would certainly fit inside this box. Notice I do have plus or minus. So this works also if x is a negative number. But what's a negative distance? Utterly meaningless in our dimensions. So we throw that negative value out. We only use the positive one. So the quadratic formula tells us that x is 42.4. How wide is the strip of lawn? Well, let's take a look. So now our diagram looks like this. It's 60 by 80, and we have a factory in here that's 42.4 wide. So what's the gap between that and 60? And we'll split that in half. So if I go in here and I make this number negative and add it to 60, that's going to give me the width of the lawn, but twice of it, 2 times the width of the lawn. That's this distance plus that distance. And together that would make 60. So I need to divide this by 2. And so it's about 8.8. Therefore, the lawn is about 8.8 meters wide. Whew. Sorry, I looked at that question, thought I had a road to a solution, then very quickly had to change my road to a solution. Okay. So, skip this. We'll actually do this tomorrow. This lesson's gone on for long enough. This part will be for tomorrow. Take a look at questions 9 to 13 in page 162 of your textbook. Will help you apply some of the ideas that we've just looked at today. Some of the other ideas that we should talk about, and I'll do this visually in Desmos, is if you want to know things like for how long is the rocket going up in the air, there we need to actually find the vertex. You can still use a quadratic formula to find this vertex using negative b over 2a to find the x value of the vertex. And then you would know the rocket is rising from this initial value all the way to the top. That's the period where the rocket is rising. The rocket is descending after that, and it becomes negative values after it lands. So these are just some ideas that come from looking at these pictures and analyzing these pictures. Any questions? Send me an email or bring me over to your tables today and we'll try some of these practice problems in the textbook.